I don't know about you, but I love rotations. A rotation is a type of motion about a given axis, and it is used in many different mechanical systems. We can describe its motion using momentum, which is the amount of velocity that a given mass has. At least, this definition is true for linear momentum, or momentum in a straight line. Let's get my little brother to help us understand this.
On ice, friction is very limited, meaning that the system is almost isolated. When I push on Ivan, he accelerates to a certain velocity. The product of this velocity and his mass is known as his linear momentum.
Angular momentum is alike to linear momentum, except for it is a product of the angular velocity, or the velocity of a rotation, and the moment of inertia.
Wait, you don't know what moment of inertia is?
To understand this, let's think back to linear movement. In linear momentum, mass is the total resistance an object has to linear movement. Well, moment of inertia is like that, except for it is the total resistance an object has to, well, rotational motion. Let's consider a mass with negligible size.
This is what scientists refer to as a point mass, and can be used to find the moment of inertia. The moment of inertia is just this mass times the radius about the axis of rotation squared.
However, objects like this basketball are not point masses.
But if we break the ball up into several point masses, then its total moment of inertia is equal to the sum of every moment of inertia of all the point masses in it.
So if the radius of the ball was smaller, like this lacrosse ball, then the amount of mass will be distributed much closer to the axis of rotation. This means that the moment of inertia is smaller, and it will be easier to rotate than the basketball. Figure skaters use this all the time. For example, when they turn, they might start with their mass distributed very far from the axis of rotation, in a position such as an arabesque. When they pull themselves closer to the axes, they end up accelerating. Well, this is due to what is known as the conservation of angular momentum. In an ideal system, such as the one that is very close to what they have being on ice, like I stated before, the angular momentum of their rotation will be conserved. So if we look at angular momentum as the product of the moment of inertia, or I, times the angular velocity, omega, then we know that if this is to be conserved, that the product of these two needs to stay the same. So if the moment of inertia gets smaller, then the angular velocity needs to get bigger to keep the product the same as it was at the beginning of the rotation. Like figure skaters, engineers use the conservation of angular momentum for many different applications of rotational mechanics. Understanding this principle and just rotations in general is essential for understanding these mechanical systems in our world.